Hello, everyone. We are ready to jump into Unit 9, which is all about solving exponential and logarithmic equations. So before we can jump into solving them, we want to look at some of the properties that we'll be using to solve them. So this first section is all about the basic properties of logarithms. Okay, so I just want to kind of remind you, when we finished graphing logarithms, remember we started with something like a to the x power, right? We started with the exponential form, and remember exponential functions either look like this or they look like this, right? Either increasing or decreasing, or exponential growth or exponential decay, right? And then whenever we swapped it and made it look like a log, we ended up with something that looked like this, right? Or something that looked like this, right? So remember with exponentials, they all go through this point right here, which is 0, 1, right? 0, 1, because anything raised to the 0 power equals 1, okay? So whenever we take those ordered pairs and we swap all the x's and we swap all the y's, then what we end up with on our log graphs is the point 1, 0, okay? And that's true for any log function in its most basic parent form here, is that it will go through this point 1, 0. So what we're going to look at today is this idea that logarithms and exponentials undo one another, right? They're inverses. So just like a square undoes a square root, or addition undoes subtraction, a log undoes an exponential base, okay, as long as the log base is the same. So I want to show you this inverse property, and then we'll go back to these basic properties. Okay, so this inverse property is showing that. It's showing that if we have a log base b, so whatever that little base happens to be, if we have an exponential base, right, or a number whose base matches that log base, those are just going to cancel out. I know we talked about this a little bit on the previous unit. Okay, those will just cancel out. Whatever number you have up here in your exponent, it just comes down, and that's what this will equal. Okay, the same thing is true if you go the other direction. If you have an exponential base b, and up in the exponent you have log base b, then exponential base b and log base b will cancel, and you'll just be left with that number inside the log. So for this example, our base is b, right? So when we have b log and b exponential base and they're evaluating one another, they cancel out, okay? So let me just show you what this looks like. If we had log base 7 of 7 to the x power, okay, our log base 7 and 7 would cancel, and this would just equal x, okay? Or if we had 7 raised to the log base 7 of x, okay? Because here I have an exponential base 7, and up in its exponent, we have log base 7. So again, those are going to cancel each other out, and I'll just be left with x, okay? So these work. Yay, okay? Now, let me show you what doesn't work. What doesn't work is if you had something like 7 times log base 7 of x, okay? This does not equal x. And the reason is, notice here, this is just 7 times that, okay? This is just a multiplication, and it happens to be that you're multiplying by the same number that your log base is. But you're not composing those functions, right? Notice here, the 7 is inside the log. Or in this one, the log base 7 is inside the exponent of this. So they have to be evaluating one another, right? Or the exponential base has to be inside the log, or the log has to be up in the exponent, for these to cancel out, okay? It can't just be something like this. It also can't be something like log base 7 of x to the 7th power, okay? That does not equal x, okay? Because notice here, even though I have a base 7 and I have a 7 exponent, this base is x, okay? The base inside the log and the base of the log have to be the same in order for those to cancel out, okay? Does that kind of make sense? All right, so these are two properties we're going to use a ton when we're solving both exponential and log equations. Okay, so it's good to be aware that anytime you have a log base and an exponential inside where the base is the same, it cancels, or if you have an exponential base raised to that same log base, those will cancel. Okay, now notice here on this one, when we cancel our log base b and b, whatever was in our exponent is what we're left with, right? So this basic property up here is very similar to that. Notice here I have log base b and b, so that should cancel, but we're not left with 0, right? Because we started with something, it doesn't just go away. So I want you to think of when there's no exponent written there, like here we had an x, you gotta think about how many b's do I have here, right? And I have 1. This is b to the first power. So when I have log base b of b, I can cancel those, and whatever the exponent is here is what I'm going to be left with. Okay, so this rule, and this rule are basically the same. The only difference is this is just b to the first power, which means it'll be equal to 1. This is b to some other power, which means it would just be equal to whatever that other power is. Okay, and then this other basic property is what we get by looking at these graphs. This just says if I evaluate any log at the number 1, it should equal 0, right? Which is true because every exponential goes through 0, 1. So when I swap it, every log should go through this 0.10. So if I plug 1 into any logarithm, it should equal 0, okay? All right, so these are things that are going to come in handy as we simplify, and we'll revisit these as we need them. But I want to show you now kind of how to use this inverse property to simplify. So let's look at these examples down here at the bottom of the page. The first one is log base 2 of 2 to the third power, right? So notice here I have log base 2 and I have a 2, so I just have to make sure, are these something that will cancel, like my two examples up here at the top, or are these two things that are not evaluating one another and will not cancel? So since I have a log base 2, I need to make sure that in order for it to cancel, that my base inside the parentheses is also a base 2. And it is, right? This is an exponential base 2. So here my log base 2 and 2 will cancel, and this will just equal 3. Okay. Same thing on this next one. We have 7 raised to the log base 7 of 10. So I do have an exponential base 7. In order for the log base 7 to cancel this exponential, it has to be up in the exponent of that 7. And here, notice it is. So my 7 and my log base 7 are going to cancel, and this would just equal 10. Okay, so you'll see it in many different ways. Sometimes you'll have it in log form where it cancels. Sometimes you'll have it in exponential form where it cancels. Okay. All right, and then I want to show you just a couple with the natural log. Okay, remember the natural log, ln x, is the same thing as log base e of x, right? So anytime you see ln for natural log, that just means we're talking about log base e. And I don't know why I did a squiggly. It's not approximately equal to, it is equal to that. Okay. So what this is saying is basically we have e raised to the log base e of 27. Okay, and when we have an exponential with a log with that same base in its exponent, they cancel. So this will just equal 27. Now I don't mind if you write log base e if that helps you to see that this is an e and that's an e and you can cancel them. But it's really good just to get used to knowing that ln is log base e, and that anytime you have an e evaluated at an ln in its exponent or an ln evaluated at e, that those are inverse functions and will cancel. Okay, so same thing on this next one, ln e, remember this is log base e of e to the 14th. My log base and my exponential base inside the log match, and so they cancel, and I end up with 14. Okay. Or again, if it's just written as ln of e to the 14th, ln and e cancel, and I'm left with 14. Okay. All right. Let's look at one more at the top of the next page, and then I'll have you all try some. So this one says, which of the following equations uses the inverse property of logarithms correctly? Select all correct answers. So we're looking to see, does the log base and the exponential base match, and are they evaluating one another? Meaning, is the exponential base inside the log, and is the log up in the exponent of the exponential base? Okay, do they cancel out? So if I look at this first one, I have e raised to the ln. Well, yes, e is evaluated at ln. So these two are going to cancel out easily, and we'll be left with 8. So this one does represent that inverse property of logarithms. Okay, if we look at this next one, I have ln of 8 to the e power. Now, in order for this ln to cancel out, I would have to have an e base inside the log, and I don't have an e base. I have an e exponent, but I don't have an e base. I have an 8 as my exponential base. So this one is not representing the inverse property because it will not cancel out. Okay, when I look at the next one, this one's very similar to the last one, right? In order for this ln to cancel out inside that natural log, I would need an exponential base e. I don't have base e here, I have an 8. And so 8 and ln do not cancel one another. Even though I have an e in the exponent up here, in order for the log base e to cancel, or the natural log, I would have to have an e inside of it. So that one doesn't work. Okay. And then notice our last one here, this is what I was looking for, right? ln evaluated at e to some power. This ln and e will cancel, and it will just give me 8. So the first one and the last one are the two that demonstrate that property correctly. Okay. All right. So at the bottom of the page here, there are some practice problems for you to try. There's 1, 2, and 3. So I'm going to have you go ahead and, excuse me, pause it so you can work these out. And whenever you get done and are ready to check yourself, or if you get stuck and need a little bit of help, go ahead and unpause it and we'll go over them. Okay, so let's go ahead and go over them. On the first one, notice here, the log base 13 is in the exponent of our exponential base 13. So these will cancel, and this just equals 72. Okay. On number 2, I have log base 4 of 4. That should cancel. But notice, if you're not sure what you should be left with, make sure your inside value, that 4, is written with an exponent. Here we have 4 to the first power because we just have 1 4, right? And then when we cancel our log base 4 of 4, this should just equal 1. Okay? All right, and then on number 3, we want to see which of these accurately, hold on, let me get rid of this. There we go. Okay, which one of these accurately shows the inverse property of logarithms? We're looking for, do we have a log and an exponential that will cancel each other out? Okay, so I look at this first one and I have 5 raised to log base 9. These are kind of hard to see. I'm going to write them out to the side. 5 raised to the log base 9 of 9. Okay, so notice this 5 in the log base 9, that's not going to cancel because this is a base 5 and that's a base 9. However, up in the exponent, I have log base 9 of 9. So that's going to cancel, right? This is 9 to the first power. So when I cancel log base 9 and 9, I end up with 5 to the first power, which is then just 5. Okay, so this one does accurately show the inverse property of logarithms. Let's look at the second one. The second one is 5 raised to the log base 5 of 9. Okay, so notice in the exponent, this one's not going to cancel out like the last one because I have log base 5 of 9. Those bases don't match, right? But if I look at my exponent, or sorry, my exponential base, which is 5, my 5 is raised to the log base 5. So these will cancel, and this will just equal 9. So this one also represents the inverse property of logarithms. It's just in these two cases, they canceled it in different ways, right? This one canceled in the log up in the exponent. This one canceled with the exponent and the log that is within it, right? All right, let's look at this next one. This next one is 9 raised to the log base 5 of 5. Well, here my 9 and my log base 5, those are not going to cancel because they don't have the same base, but my log base 5 of 5 cancels, right? That would just become a 1. So I get 9 to the first power, which is then just 9. So because I was able to cancel inverse functions here, this one accurately shows the inverse property of logarithms. Okay, when we look at this next one, we have 5 raised to the log base 9 of 5. Notice my exponential base and my log base do not match here, so those do not cancel. And then if I look within my exponent, I have log base 9 and base 5. Again, they do not cancel, so this one does not represent the inverse property of logarithms. When I look at the next one, I have log base 5 of 9 to the 5th power. Notice this is log base 5. Inside that log, I do not have an exponential base 5, so these do not cancel. Okay. And then my last one, I have log base 5 of 5 to the 9th power. Again, I have a log base 5, but this time I have an exponential base 5 inside of it. So those will cancel, and this will just give me 9. So this last one is also a solution. Okay, we're kind of okay. So this is our idea of exponentials and logs being inverses and how they can cancel one another out. Okay, so now what I want to look at is I want to look at some properties or rules or whatever you want to call them of logarithms that we're going to use when we get into solving equations. So I want to just get familiar with these rules and properties in this section, and then in the next section we'll do a little bit more with them. Okay, so the first one is a one-to-one property, and we will use this one a lot in both directions. And this states that if we have log base b of m is equal to log base b of n, so we have the same log base on both sides. If these two logs are equal and they have the same base, that's only true if the little numbers inside of them are also equal. Okay, so that means if we have two equal numbers, we can slap a log on both sides and it will maintain its equality. Or if we have two log terms that are equal to each other, as long as they have the same base, we can actually just drop the logs and make the assumption that the numbers inside those logs have to be equal. So we'll see that one a lot more here in a couple sections. Okay, for now I'm going to kind of focus on these guys, which is the product rule, the quotient rule, and the power rule. And what this allows us to do is to rewrite a logarithm, one logarithm, as several logarithm terms, or to take several logarithm terms and condense it down to one logarithm term. Okay, and we only have 3. So you got to keep an eye out because there's times you might want to hope that there's a rule, but we only have 3 of these rules. So the first one is the product rule. The product rule says that if we have a multiplication inside the log, that multiplication turns into an addition of log terms. So log base b of some m times some n, I can rewrite as log base b of m plus log base b of n. So I can separate it into 2 log terms if we start with a multiplication. Now we'll use this both directions. So if you see a multiplication, we can split it into 2 log terms, or if we have 2 log terms that are being added, we can condense it back into 1 log term that has multiplication. Okay. Same thing with the quotient rule. This time it is with division. So if we have 2 things being divided inside the log, we can turn that into 2 terms that are being subtracted. So notice, the one that gets subtracted is the one that comes from the denominator. Okay, that's very important. Some of these multiple choice homework questions will write it out like this, but they might say log base b of n minus log base b of m, just to try to trick you. So don't be tricked, okay? Make sure that the one that's being subtracted is the one that came from the denominator of that value inside the log, okay? All right, and the last rule that we have is that if we have log base b of m to some power, so notice this power is being applied to this entire whatever's inside here, okay? So if this power is applied to the whole inside number, we can actually take this power and bring it down as a coefficient in the front. And the reason that we can do that is because of this multiplication rule. Let's say this was m squared, okay? Let's just say this was log base b of m squared. M squared means I have m times m, right? So let's just pretend that this says m times m. If I say m times m, if I have two m's, m squared, right? That's a multiplication, which I could then break into an addition. So I would have log base b of m and another plus log base b of m, right? So that would mean I would have two terms that look identical. So they would be like terms. So instead of writing them separately, I could add them together and say, okay, well, that will equal 2 log base b of m. Okay, or in other words, that squared that we had that showed repeated multiplication, when we expand that multiplication, we're going to end up with as many terms of the same log value. So we can just count up how many terms we have, and that's going to be the coefficient here on how many of those log terms we have. Okay, so this is just condensing, helping us not to have to go through this step first. Okay, all right, so let's go ahead and look at some examples. This says, which expression shows log 15t minus log 5? So if I have log of 15t minus log of 5, and notice my choices here all have one log. So I want to condense this, okay? So I want to condense, and since it is a subtraction, right, we get subtraction from starting off with a division inside our log, okay? So I'm going to say condense to division, okay? That means I can write it as one log term, but then stack in a division way my two inside numbers. And remember, the one that gets subtracted is the one that ends up in the denominator. So this is going to give me 15t over 5. And then, I mean, I'm pretty much done, but I do want to see if this simplifies. 15 and 5 reduces, so I want to make sure I do that. So this just gives me log of 3t. So then I just look for my answer over here, and that should be my third choice. Okay? Let's look at another one. This next one says, which expression is the expanded form of log base 4 of 6 times 5 plus 2x? So, expanded means I'm starting with one log term and I want to expand it. So remember, we only have 3 rules. We have a rule for multiplication, we have a rule for division, and we have a rule for exponents. So if I look at this one, what I can see inside this log is that we have a multiplication, right? This is 6 times this quantity. And remember, multiplication gets separated into addition of log terms. So I can rewrite this as log base 4 of 6 plus log base 4 of 5 plus 2x. Okay, so the two things that are being multiplied here are the two inside values that we're going to have when we split this into an addition of log terms. And then I just need to make sure that these are completely simplified. Notice here this is log base 4. This is an exponential base 6. Those do not match. This is not going to cancel. Okay, same thing over here. Now, a lot of times people see this addition and they want to split that into 2 log terms. But if you look up here at the top of our page, we only have rules for a multiplication inside the log, for division inside the log, and for an exponent. We do not have any rules for addition inside the log. So if we get down to where we have log of an addition quantity, we can't go any further. Okay, so now that we've split this into 2 terms, that's as far as we can go. So we just determine which of the choices here is the correct one. And here it should be our second choice, right? All right, let's look at a few more, and then I'll have y'all try some, okay? All right, this one says, which logarithm is equal to 5 log 2? 5 log 2, okay, or 5 log of 2. I like to use parentheses. All right, So now that I have it written out, remember I'm looking for a multiplication inside the log, a division inside the log, or an exponent. And I don't have anything inside this log except for a 2. So there's nothing to expand here. So if I can't expand this into more log terms, then I guess they're assuming I can condense it more. And the only thing I have to condense is this 5 that's out front. Remember, we had that property that says we can take the exponent and bring it down in front of the term. So that means if I have a coefficient in front of the term, I can actually put it back up into the exponent. So that's what I'm going to do. I'm going to put this 5 back up into the exponent. So I get log 2 to the 5th power. And then if we look at our choices here, we don't have any exponents, right? So that means I need to go ahead and multiply this out. Log of 2 to the 5th power gives me log of 32. And that is my 4th choice here. So that is my answer. Okay? All right, let's look at another one. This one says, which expression is the expanded form of log base 7 of 4y plus 7 over y minus 2? So here, when I look inside this, I'm looking for a multiplication, a division, or an exponent. And the only thing I see here is that I have a quantity on top of a quantity with a fraction line. And remember, that fraction line represents division. And division can be expanded and broken into separate terms by subtracting. Remember, the one from the denominator is the one that's going to get subtracted. So I can rewrite this as log base 7 of 4y plus 7 minus log base 7 of y minus 2. Okay. Again, I always check to see if I can go further. When I look inside my quantities, I have an addition and I have a subtraction. We don't have any rules for addition or subtraction inside the log. We only have rules for multiplication, division, and exponents inside the log. Okay, so this is as far as I can go. So that I just want to choose the right answer, which I can tell is going to be either the 3rd or 4th choice. Make sure you know which one is negative. The negative one is the one that always comes from the denominator. Okay, so log base 7 of y minus 2 should be the negative term, which means that this 3rd choice is the correct one. Okay? All right, let's look at this next one. Same idea. I'm looking for a multiplication, a division, or an exponent. In this one, the only thing that I have is an exponent, which means that I can expand this just a little bit by taking that exponent and bringing it down as a coefficient. So I end up with y times log base 9 of 2. Okay? And that's all I can do here because I don't have a multiplication or a division, and I no longer have an exponent. So this is my most simplified version of this, which is my 2nd choice over here. Okay? All right, let me look at one more, and then I'll have y'all try some. So on this one looks a little bit different because we're still looking for an expression which is equivalent to this log, but what's kind of disconcerting here about this log is that we have an addition, and we have no rules for addition inside the log, right? We only have rules for multiplication, division, and exponents. So if I look at this, there's no way I can write this as something raised to some power, right? There's also, I'm not seeing a way to write this as a division. So the only thing I can hope to do is maybe write this as a multiplication. So I want to see if I can write this in a way that it represents multiplication, right? And the backwards version of multiplication, right, is factoring. So I'm going to look for a greatest common factor, which in this case, they are both divisible by 2. So I'm going to factor out a 2, and I will be left with not 8. I will be left with 4x plus 5y. Okay, so now that I was able to pull out a greatest common factor, now we have a multiplication in here, right? I have 2 times a quantity, and multiplication expands into addition. So I can write this as log of 2 plus log of 4x plus 5y, right? And then from here, I just double check to make sure I can't go any further. This is log base 10 because there's no number written there. 10 and 2 are not going to cancel. And then here, I can't go any further because I have an addition inside here, and there's no greatest common factor for what I have listed here. Okay, so I just want to choose this solution over here on my answers, and it is my third choice. Notice they put some tricky ones in here, right? This one looks identical. The only difference is that multiplication. So make sure you're clear on multiplication inside the log becomes addition of log terms, okay, not multiplication. All right, so there are 4 for y'all to try. There's 3 on this page and 1 on the next one. So I'm going to give y'all just a second to pause the video and work those out, and whenever you're ready, play it again and we'll check you. All right, so on number 1, the only thing we can do with this expression is take that 7 that's in the exponent and bring it down in the front. So we end up with 7 times log base 2 of 3, which is our first choice here. Okay, we look at our second one, and we have an expression which we can condense. Notice we have an addition of log terms. Addition we get when we have a multiplication inside the log. So we're going to condense this to multiplication. So I can write it as 1 log term where my inside numbers from those 2 terms are just multiplied. And 3t times 4z gives me 12tz. So that is my second choice over here in my solution to number 2. Okay. All right. Number 3, we want to expand, but we can only expand it if we have a multiplication, a division, or an exponent. Here we don't have any of those. So I'm going to work this one like I did that last example where I look for a greatest common factor. I have a greatest common factor of 3, so I can write this as the natural log of 3 times that leftover quantity, which is 2a plus 3b. And now this is a multiplication, which I can expand to addition. So I'll get natural log of 3 plus natural log of 2a plus 3b, which is my third choice here. Okay, so far so good, hopefully. And then number 4 wants us to find the equivalent expression for log base 3 of 5 over 7. Now, even though this is just a regular number, right, it's still a fraction. It still represents a division. So we can expand that into subtraction, which becomes log base 3 of 5 minus log base 3 of 7. That's all we can do. We can't go any further because my 3 and my 7s or my 3 or my 5 is not going to cancel. So that's the first choice on number 4. Okay. All right. So that concludes this section, which is basic properties of logarithms. So you should now be able to complete that assignment on your Knewton Alta homework. And if you have any questions, please let me know.